Welcome back, everybody. We're going to move on to section 6.6 in the book. That deals with rational exponents. Rational just means fractional. So we can imagine expressions like x raised to the 2/3 power or y raised to the 7/4 power. The point of this section is trying to figure out what do these fractions as exponents mean, and how do we simplify expressions that have them. We've spent a lot of time over the last couple of sections simplifying radical expressions. But what we're going to find in this section is that rational exponents are radicals. They're just another way of representing radicals. I'm going to show how this works, but first let's go back and remember a couple of the important rules about exponents. In the case where I have a common base, a here, and I multiply two expressions of a raised to powers, we add those exponents. In the case that I have common bases and I'm dividing, we subtract those exponents. If I have a negative exponent, all that means is that I'm taking the reciprocal of a to that exponent. So here, a to the negative x should be the reciprocal of a to the x. And as we know, taking the reciprocal just means putting it under 1 in a fraction. The last property I want to talk about, and the one we've been talking about most in the last couple of sections, is this. What happens when I have a number raised to a power, and then I raise that entire expression to another power? Well, in this case, instead of adding the exponents, we multiply the exponents. That becomes a raised to the x times y power. In fact, the whole point of fractional or rational exponents is to make it easier to deal with simplifying some of these expressions involving radicals, because we can apply these exponent rules very easily when we have numbers that are easy to add or multiply. But it's a little bit more difficult to deal with things written in this style. As we've seen, trying to add or multiply these kinds of expressions involves a lot of algebraic manipulation, and we're trying to make that just a little bit easier. The classic example of how fractional exponents work has to do with squaring and taking the square root. We know that taking a square root and squaring something, these are inverse operations. So we want a way to make this fit with the exponent rules so that it also fits with the inverse function rules. If I have a function, f of x, where all f does is square x, we know that the inverse of f is the square root of x, because if I input x into f, and then input that result as x into f inverse, I get x out. In other words, as we expect from inverse functions. But let's make this fit with all of these exponent rules. Since f is raising x to the second power, we can think of f inverse of x as raising that expression to another power. So when we take f inverse of x squared, and we expect to get x out, what power will we have to raise the entire expression x squared to in order so that we get x out? Remembering, of course, that the exponent on plain old x is just a 1. Well, by the exponent rules, whatever's in this box gets multiplied by 2. And of course, the number we have to multiply by 2 to get 1 back is 1/2. All this is showing is that taking the square root and raising an expression to the 1/2 power are the same thing. And this is the basic idea of fractional or rational exponents. Let's take a look at this key concept. Here's where it states what we care about. Taking any number to the 1 over n power is the same as taking the nth root of that number. That's the most important definition from this section. So taking the third root of 27 is the same as raising 27 to the 1/3 power. In a variable form, let's say we have x to the 1/10 power. By this rule, that needs to be the 10th root of x, or the number that we need to multiply by itself 10 times to get x back. Well, that's a simple enough concept, but we start to see this get a little bit more complicated when we apply some of the other exponent rules. And from this basic concept, we can build everything else we need to know about rational exponents. And we can get to some of these strange expressions, like x to the 2/3 or y to the 7/4 power, and figure out what that means. Right now, we already know that x to the 2/3 power can be expressed as x squared to the 1/3 power. Why does that make sense? Because when we raise a power to a power, we multiply those exponents. Obviously, 2 times 1/3 is equal to 2/3. So we can already see that it should be the case that since we're taking the quantity inside the parentheses and taking the cube root of it, that we should end up with the third root of what's inside the parentheses. And what's inside the parentheses happens to be x squared. So you can already see that using these rational exponents is just a translation for things that we've already seen in nth roots. Here's the definition that we need to actually talk about all rational exponents. And this part is the key component of this definition. When we take a number and we raise it to a fractional power, that's the same as putting the numerator inside the nth root and then putting the denominator outside the nth root. Let me explain what I mean by that. If we look at the number 2 to the 3/2, the numerator of the fractional exponent gives us the power on 2 that we're dealing with. So we're dealing with 2 to the 3rd here. The denominator tells us what root of 2 to the 3rd we're taking. So first, we can consider what's happening inside the nth root. And second, we can consider what's the nth root that's being taken. So in this case, what we end up with is 2 raised to the 3rd power, and then the square root taken of all of that. So these are the same expression based on this definition. Now we're used to seeing this second expression. We've seen it many times with both numbers and variables, but we need to be able to translate that into a fractional exponent. By the way, we can simplify this if we want to. This is just the square root of 8, and the square root of 8 is a reducible radical. We've got a perfect square hiding in that 8. It's 4 times 2, so we can pull the 2 outside of the square root, and that leaves us with 2. We could, I suppose, also write 2 times the square root of 2 as 2 times 2 to the 1/2 power. And again, this makes sense with the rules that we know for exponents. This is 2 to the 1st power times 2 to the 1/2 power. And when we multiply common bases, we add exponents. That's how we get back 2 to the 3/2 power. So all of these things mean the same thing. We're trying to find a way of making use of all of this to make some of our simplifications a little bit easier. Make sure to take a close look at this example, which does the same thing we just did with 27 to the 2/3 power. So if we want to look at this as variables, consider the expression c, some number raised to the 5/3 power. Well, the 5 is the power to which we're raising c, so inside our radical we're going to have c to the 5th. Outside the radical, we care about that denominator as the root that we're taking. So here we're taking the 3rd root of c to the 5th. We can also look at this as being c to the 5th power raised to the 1/3 power, or even c to the 1/3 power raised to the 5th power. Since it doesn't matter how we do the multiplication of the exponents, these are all going to be equivalent expressions. So whether we take the root first and then raise it to a power, or we raise it to a power and then take the root, we're going to end up with the same thing. But in any case, we're going to end up with c raised to the 5/3 power. Negative exponents also have a role to play here. Since negative exponents are just reciprocals of positive exponents, we can end up with expressions like this, 81 to the negative 1/4 power. All the negative means is that we're taking this entire expression and putting it on the bottom of a fraction. That's 1 divided by 81 to the 1/4 power. Well, let's translate this into a form that we're more familiar with. 81 to the 1/4 is the same as 81 to the 1st power raised to the 1/4 power, or the 4th root of 81. Well, we know what the 4th root of 81 actually is. This is just 3. So this entire expression reduces to 1/3. But the same thing is true no matter how complex our argument gets. This crazy expression is actually pretty easy to simplify. The first thing we do is notice the negative exponent. That just means take everything and put it on the bottom of a fraction. Well, let's write this in a form that we're more familiar with. Well, that makes sense. But let's see if we can simplify this a little bit. All I did there was distribute that square to each of the variables. Now the question is there anything we can remove from that third root? Sure. Both a to the fourth and b to the third have perfect cubes hiding in them. We can pull this entire term b to the third out, and we can pull 3 of the 4 a's out, which is going to leave 1 of the a's behind. We can't do anything with the c squared. Let's see what we end up with. Now this is a partially simplified expression. We're going to talk in just a little bit about how we need to do more with this because we don't want to have these radicals in the denominators of fractions. But for right now, all I wanted to show you is that we can deal with negative exponents for variables as well as any regular numbers.